Let's look at an application example. The frequency content of an audio signal changes naturally as a function of time. So it's important to have the ability to observe such changes when analyzing a signal. Spectrograms are used as the graphical tool for this purpose. In this example, we create a rudimentary spectrogram that will be created using the so-called short-term Fourier transform, which basically calculates the Fourier transform that you're already familiar with, but over short segments of a signal. Given the frequency content of each segment, we assemble the individual Fourier spectra in a matrix and display the data using any suitable 2D plotting routine. Here's a simple time-varying sequence, and we can listen to the audio version of this sequence. Now let's look at a shortened version of our sequence to see how it changes over time. Now let's divide this sequence into non-overlapping segments of length n equal to 50. If we get a 3D plot of the partitioned sequence, we can see that we have multiple segments. We have the lower frequency sign followed by a higher frequency sign and ending with a so-called chirp sequence, which has a linearly increasing frequency. Now let's compute the magnitudes of the Fourier transform of each of these segments. For this purpose, we can use the function Fourier, and it will return the most basic version of a short-time Fourier transform. The partitioning and the evaluation of the Fourier transform of each segment can be obtained by directly applying the built-in function short-time Fourier to the sequence. We can plot the magnitudes of the Fourier transform in terms of frequency and time. We could also use array plot in the Wolfram language to get a rudimentary but perfectly usable spectrum, as shown here. The horizontal axis denotes the time, and due to symmetry, only half of the Fourier coefficients are shown. Now, instead of all this, we could use the built-in function, a spectrogram, and it nicely shows the frequency content of the signal, as shown here. In this application, we looked at the spectrogram of an audio signal, which is the visualization of the frequency content of the signal as a function of time. We created the spectrogram using the what's called short-term Fourier transform of the signal, and then we compared the spectrogram that we created to the result obtained by the built-in function in the Wolfram language.